Yes, so I'm trying to develop from what we have here. I let the reason why I call this equation 1 is there's something else I want to derive from here. So assuming that asked us for the relative error in A. Yeah, the expression for the relative error in A. So you should know that relative error is the error divided by the exact value. So I got from equation 1, I divided through by A. But remember, A is small l times small w. So on simplifying that, you find that your relative error is equal to the sum of the individual relative errors in the length and in the width. So again, this is where you apply the triangular inequality, that the relative error you would make if you determine the area using a certain instrument. This is just an analogy now. Would never be bigger than the sum of the individual relative errors in the length and in the width. That's the analogy. So that's why we apply the triangle inequality. Yes, the absolute value in the relative area. The absolute value of the relative error in obtaining the area will be less than or equal to the magnitude of the sum of the different relative errors. Or it is the same as saying that absolute relative error is less than or equal to the sum of the individual absolute relative errors that were determined. So it is either less than that or equal to. But if you want the maximum, then you have to take that is equal to, because the maximum relative error will never be bigger. Yeah, practically, if it's done practically, you would find that it will never be bigger. So that means the maximum possible relative error is that the sum of the individual relative errors. Therefore, with that, there is a quiz. And this question says the height and the radius of a cylindrical water tank are given by that and that. So, respectively, yes. So, what I want you to notice here is they've given you the error bounds in that delta H is 0.2 and delta R is 0.1. And then the exact values also you have the 3.5 and then 1.4. So they say determine in meters cubed the least and greatest amount of water the tank can contain. Hence, calculate. So I think that's supposed to be calculate the maximum possible error. Hence, this calculate. I don't think it's calculate. But what the point is, what I want you to do, what I desire that you do is you introduce unknowns. For example, they have this capital H and capital R are approximate values. That's what I want you to see. These are approximate values in the radius and in the height of the cylindrical water tank. This is a cylinder. That's basically we're dealing with. If that is the approximate value, then let the actual value be small h and small r. And then the errors are respectively delta h and delta r. So I want you to play around with these definitions or these unknowns. Small h. First, ignore the actual values. Yeah, small h, small r, delta h, and delta r, and obtain for me an expression for the maximum possible error in calculating the volume of this cylindrical water tank. And get that expression, yes? So I'd expect you to have something like this. If let's say you let the volume be V, I expect you to have something like this. Then you get me what is in those modulus bars, what is here and what is here. Then I would also test, I would want you to prove it on your own. That after obtaining this, yeah, you're going to obtain this expression. So now somewhere you're going to have h, somewhere you're going to have these 4. In the expression, I'm definitely sure of that. Yes, there are 4. You're going to get, let's say you're going to call it your first solution, and your second solution. So you're going to get the maximum possible error. The maximum possible error. Your first solution, I want you to use this expression. Now, in your second solution, I want you to use the first things or the first principles we looked at. The first principles we looked at, and you would see that your answers are going to converge. Are going to be quite similar. So I want, in the second solution, use the first principles that we saw. Yeah, we use the first principles that we saw. But in the first solution, you're going to use this expression you obtained, and it would give you the same answers that you'd get in the second solution. Remember, 3.5 is small h, 1.4 is small r, because those are the exact values. And the respective errors is delta r is 0.1 and delta h is 0.2. Yes, so, and remember it is volume because I want you to find in meters cubed. So with that, I think I will end here. And I think that summarizes errors. So, but there are some questions concerning trigonometric functions, and they're also under error propagation. A few are going to be posted, and you may go through.